So, good evening, everyone. So, welcome to my YouTube channel, Math Sastram. So, today we are going to see very important theorem called Euler's theorem for homogeneous function. So, let's see what is that theorem. Let f(x, y) be a homogeneous function of degree n in variables x and y, then x and y such that first and second order partial derivatives derivatives of f are continuous. Then we have x del f upon del x plus y del f upon del y n times of f, and x square del square f del x square plus 2xy del 2f del x del y plus y square del 2f del y square is equal to n into n minus 1 f. Okay, so let's prove it. So let's prove it. So how we will prove it? Since f is a homogeneous function of degree n in x and y, therefore f x y is equal to x to the power n g y upon x, where g y upon x is also a homogeneous function of degree 0. So this is also homogeneous function of degree 0. Okay. Now let's say it 1. So Del f upon del x, what is this? This is nothing but n times x to the power n by g y upon x plus x to the power n g dash y upon x minus y upon x square. So what is this? X n into n x to the power n minus 1 g y upon x, and this is minus y x to the power n minus 2 g dash y upon s. Let's say this is equation 2. Similarly, we can what is del f upon del y? Del f upon del y is nothing but x to the power n g dash y upon x into 1 upon x. So this will become x to the power n minus 1 g dash y upon x. Let's see third. From 2 and 3, we get what we get? X del f upon del x plus y del f upon del y. What is this? This is n x to the power n g y upon x minus y x to the power n minus 1 g dash y upon x. This is the value of this the x del f upon del x. Now, what is this value? This value is nothing but y x to the power n minus 1 g dash y upon x. So this factor is cancel out. So what we got? So we got x del f upon del x plus y del f upon del y is equal to n x to the power n g y upon x. But this is nothing but fxy. So this implies x del f upon del x plus y del f upon del y is equal to n f. Okay. So this is true. Let's say this equation is star. Now taking partial derivative both the side of 1 of star, we get what we get? X so what we got? Del f upon del x plus del 2f del x square, okay, plus y del 2f del x del y, okay, and times del f del x. Let's say it 4. This equation is 4. Again, taking partial derivative both the side of star, we get what we get? With respect to y we are taking, so x is constant, so del to f del y del x, okay. plus del f del y plus y del to f del y square and times del f del y. That's it. It's 5. Multiplying multiplying by x in 4 and by y in 5, then adding we get what we get. So this will be x square del to f del x square plus xy del to f del x del y plus del to f del y del x plus del y square del to f del y square plus x del f upon del x plus y del f upon del y and left hand from there x del f upon del x. This is x plus y del f upon del y. Okay, so let's say it's 6. Let's say this equation is 6. Now, since del to f del x del y and del to f del y del x are continuous, because in statement of theorem is given the second order partial derivative are continuous. So we get both are equal. Okay, from 6 we get using star, what we get x square del to f del x del y square. Okay, plus 2xy del to f del x square. Okay, y square del to f del y square plus f, and here is n times, what is this? So this is n, this is nf, and this is nnf. So what we got after solving it, what we get is, so this is del y square. Okay, del y square. You take, so this is here nf and this is n square f. So after solving it, what you get is del to f. So this is del x del y So this is del x, del y, del to f, del x, del y square, del to f, del y square. And here you bring this side here, you will get n minus 1 f. So this is proved. Second part is also proved. Let's say double star. Okay. Okay. Let's say double star. So we have today what we have done. We have proved Euler's theorem. So today's lecture up to this. We will meet you in next lecture. Thank you very much for today's lecture. Thank you very much.